Hi, Year 11. I have no plan with this video. I've drawn a few things, but I haven't thought through what I'm going to say, so apologies if I ramble on a bit or don't make any sense. Let me know and I will go over anything in particular that you would like me to. I'm just going to go through some of the basics of reflection and refraction and the implications of those, as people were saying that they're a little bit worried about waves. So, reflection you should be aware of because you've probably been using mirrors your whole life, where light bounces off of the surface of a material and doesn't enter it. Okay, so when we are drawing ray diagrams, there are a couple of things that you just need to be aware of. Obviously, we're going to have the surface reflected by a straight line. Sorry, you will then have a normal line. And a normal line is any imaginary line that we draw dotted that is at 90 degrees to the surface of the mirror. Now, or whatever surface that we're entering. Our light ray is shown with arrows to show direction. So this is the incoming ray and this is the reflected ray. And this is the incoming ray and this is the reflected ray. You can see that wherever my ray hits the mirror, I can draw a normal line there. It doesn't have to be in one particular position, it's wherever the light hits the surface. So I get my protractor, measure 90, draw that dotted line, and then I'm going to take us back to this slightly less cluttered diagram. You can see my normal is here, my surface is this one. It's really important that you measure the right angle. So a common mistake to make is to measure this angle here, and that would be wrong. It is always the angle between the ray and the normal line. Okay, so the ray is shown by the solid line with the arrow to show the direction that the light is travelling in, because it would be really, really confusing to be drawing actual waves in that path. So we just draw a straight line to represent that. And the first thing to know with reflection is the law of reflection, which is the angle of incidence equals the angle of reflection. So whatever this angle here is, the reflected angle is exactly the same, and that's measured from the normal to the ray that you will draw. So you take your protractor, you measure the angle of incidence, and mine is 30 degrees. Okay, I'm going to count 30 more, that takes me to 60. I'm going to mark a little dot there. And from that point, that is where I'm going to draw my reflected ray to. Okay, I'll draw an arrow to show the direction. This is R, or theta R, the angle of reflection. Okay, so I equals R equals 30 degrees in this case. Sorry, my camera's really struggling to focus today. Come on. Okay, now this could be any angle. So I could send in another ray to exactly the same point, and the angle of incidence is now this angle here. I measure that one when it wants to get in focus again. Come on. And you can see this time to the normal line it is 51, so I'm going to go to 102, mark my dot, and my angle of reflection looks like this. Okay, so in reflection the light always stays in the medium that it's in, so this could be air here and then this is your glass mirror. It never enters the glass. Okay, now you may see a diagram where you have an object, I've drawn a candle as my object, and a mirror to the right hand side of it, or the left, or below it, or above it, doesn't matter. And you have to work out where the image will be seen inside of the mirror. Okay, so when you look at yourself in a mirror, you can kind of see that you're at a distance behind the mirror, if that makes sense. You can see that your face is not right on the surface. So we take what we know about drawing rays and we use that to help us. I'm going to talk through the colours because I've used the colours to try and make this make a little bit more sense. Okay, so I've got a yellow line, which represents a light ray that is coming from the top of the candle tip. Okay, and then where that hit the mirror, I drew a normal line and I measured my angle of incidence. Okay, so this is my angle of incidence and this is my angle of reflection for this ray. So this is R, which is also 25 degrees. Okay. Our eyes get tricks played on them, basically, and this is how we view things. We, as humans, think that light travels in straight lines. Okay, so we assume then that this ray of light has to have travelled in a straight line. So it has to have come down backwards. So you can see I've drawn a construction line that's dotted that is running parallel to that reflected ray. Okay, and so what you have to do is you just draw a light ray coming off your object. It bounces off the mirror using the law of reflection, and all you do is you carry that line back. Okay, you can see that that's a straight line. Okay, so just draw backwards. Okay, go quite far back. You always have to have at least two lines, two rays of light coming off a point to identify where that point is. I then draw a second ray, this time it's green. Okay, the angle of incidence with the normal line here is 43. So I draw my reflected ray. Again, that's going to be 43. This is R, this is I. Incidence and reflected ray. But again, eyes think that light travels in a straight line. So our eyes think that this ray that is reflected has to have come from back here somewhere. Okay, so I'll put it underneath, it'll hopefully be a bit clearer. We assume that the light has travelled this path, and so we draw a dotted line back. Where those 2 points meet is where we see the image of this point on the candle in the mirror, which should make sense to you given that you know how you generally see images in a mirror. I then repeated the same process at the bottom of the candle. Okay, so I sent a blue light ray in at 10 degrees to the normal and it reflected. So my reflected ray is here and that is 10. And again, our eyes assume that that light ray has travelled in a straight line. So we assume that it has come from over here. Blue dotted line there. And then I've drawn a second one in purple. Okay, that was at 35 degrees. My reflected ray in real life bounces off, travels down here at 35, but our eyes assume that that reflected ray came from a straight line, and I track back. So this is where the bottom of the candle will be. Okay, now it's really important to distinguish between real and virtual rays. Okay, so any line that you can see here that is a solid ray, that I've drawn in a solid line, is real. It is a real light ray, genuinely travelling through space there. Okay, so if you put your hand there, you'll see light. Anywhere you see a dotted line is what we call a virtual ray, because it's not really real. Okay, there's no light genuinely going inside the mirror from this one. It doesn't magically do that. It's just that our eyes assume that's where the light has come from, and so this is where the image is formed. Okay, so it's a virtual ray. So that's your basics with reflection. Okay, I'm going to go for refraction next. I just want you to look at this picture first, ignore this one over here. So you can see, with my excellent drawing, you have a car. And I want you to imagine that the car is travelling in the direction of the arrow that you can see, and it's got 4 wheels and it's travelling on a smooth road. But it travels towards a whole load of mud. By the time it reaches the mud, hopefully you can see that given the angle that it's travelling in, one wheel will hit the mud first. Okay, so this front right wheel is going to hit the mud, and that slows that wheel down. But these other 3 wheels are still travelling at the speed of the smooth road. And so they keep going at a faster speed while this one slows down. Now, if you can imagine this one slowing down and this one continuing, it causes the car to turn. Okay? Now, that means that the car will look something like this. And instead of the light travelling, let's make sure it looks parallel. Instead of the light travelling in this direction, it's now going to travel in this direction. Okay, so there's been a bend. And now it travels through the mud, and sometime later it reaches a smooth road again. Okay, so all the wheels are travelling in the slow mud. Mud generally slows things down. It's a claggy material. This wheel now hits a smooth road first, and that wheel speeds up, while the remaining three are still stuck in the mud for a little while, which causes a turn back the other way again. And what happens is the car returns to its original direction, if it's back to the same as it was before, a smooth road, and where it was travelling like this, now it's gone back this way again. Okay, and this is an analogy to help you understand how refraction works, and it's to do with the density of the thing that is being travelled in. Okay, so I'm going to come down here, so I've not done this in a very logical order. If I travel in a more dense medium, it is slower. Waves will travel through it slower. Okay, so light will travel through it slower, sound will travel through it slower, etc. Okay, if it is less dense, it's a faster medium. Okay, and we're looking at light here. Okay, so light is slower in a more dense object, it's faster in a less dense object. That is why in a vacuum it is at its fastest rate. Okay, so c is the speed of light in a vacuum, and that's 3 times 10 to the 8 meters per second, speed in a vacuum. It's basically the same in air. It's like 2.97 or something. But you can assume it's 3 times 10 to the 8. Okay, that's as fast as light's going to go. And then as you move into other media that are more dense, so glass, water, that kind of thing, diamond, this number gets smaller. Okay, more dense, it's slower. Water works in a similar way. Shallow water is slower for waves to travel in. Deep water is faster. Now we've got this acronym, which is called FAST, which will help you to remember which way the wave will turn. Okay, if I am going into a faster medium, the wave bends away from the normal. If I go into a slower medium, I bend towards the normal. And that's really helpful for when you are drawing sketches in your exam of refraction. Okay, so you can see here I've got air and I've got glass. This is a more dense medium than air, obviously. Glass is more dense. Okay, if I'm going into a more dense medium, I'm going into a slower medium, I go towards the normal. So I know that when this light ray hits the boundary and it refracts, that means it's going to bend towards the normal. Okay, so we know refraction, hopefully from our lessons, is where wave rays change direction because they change speed. Okay, just like we saw with our car analogy. So the first thing we have to do whenever we see a light ray hitting a boundary with refraction is draw our normal line on. Obviously do it with a protractor in an exam because you want the perfect angle, but I'm just doing this for ease of sake. Here's my normal line at 90 degrees. Here is my angle of incidence. Okay, don't do this in the exam, but I just want to draw it on so that you can see what I'm talking about. If it didn't change direction, that's the line it would carry on in. But I know that it's going to bend towards the normal from the direction it was already travelling in. Okay, so the ray bends in that way. So I take my ruler. This is just a sketch, so it doesn't need to be measured. and it's bent towards the normal. So my refracted ray, which I'm also going to use an R for, it's not been reflected, but it's the angle of refraction, has bent towards the normal. But now we've got something else to consider. We have light inside of glass, leaving back out to air. Okay, so I'm going from a more dense to a less dense medium. Okay, so I'm going into a faster medium, so it's going to go away from the normal. So again, where the light ray hits the boundary, I'm going to draw my normal line. Okay, and I have a new angle of incidence, and that's here. Okay, this is at 90 degrees. But now I'm going to go away from the normal, and if you are re-entering the medium that you originally were in, so you've gone into more dense and then you go back out again, it will actually come out parallel to the original angle. So I take this one, measure it with a protractor when you do it, but I'm just for speed doing this for you. Okay, and you can hopefully see, if I draw my dotted line again to help you visualise it, here's the normal line, this one. Here's the ray without change in direction. You can see it's moved away from the normal. Okay. Now there's an equation we can use that hopefully you're seeing to help us know these angles. So the first thing we have to be aware of is this top one, which is the refractive index of a medium. So N is a value for a particular material. Okay. C is the speed of light in a vacuum. And that is a constant value. That's 3 times 10 to the 8 meters per second. Okay. This V here is the speed of light in the medium. So if you enter glass, the speed will be a lower value. The refractive index is the ratio of the speed of light in a vacuum compared to the speed of light in that medium. So you have an N value for every material, which has its own V value. Okay, that's one equation to know. And the second one is Snell's law, okay, which is N1 sine theta 1 equals N2 sine theta 2. So if I have a little glass block, and I have a light ray that's travelling through, let's call this air, I'll put a G for glass, and I know that it travels in here. I've got a theta 1, which is my angle of incidence, and I've got my theta 2, which is my angle of refraction. Okay. N1 is the refractive index of air. N2 is the refractive index of glass. Okay, and so I can rearrange this equation and say N1 over N2 equals sine theta 2 over sine theta 1. Okay, now hopefully you can see that M1 and N2 are just constant values. So this is a constant. And so you know there is a relationship between the angle theta 2 and theta 1. Okay, and that's something we're going to discuss. Alright, we're getting through it. Sorry, this is a very long video. We're almost there. Okay. Dispersion is refraction, but it's refraction of white light. Okay, white light is actually a mixture of every colour wavelength that we can see. And when they're all combined, so all of these colours here, overlapping each other, we interpret that as clear light, white light that we have all around us. But different wavelengths of light refract by different amounts because they're slowed down by different amounts. They each have different speed values in different media. So if this is a glass prism, the speed of light for red is different for the speed of light for violet light. And so what that does is it changes the angle of refraction for the different wavelengths. And so they each bend by a slightly different amount. And that splits the colours up. So then when they leave the media and they come back out into air, the light's been separated out and it travels off in slightly different directions, and you then can interpret that as a rainbow. So this is how a rainbow works. The raindrops act as the prism for dispersion, basically. Red light is refracted the least, so it bends the least, it has the longest wavelength. Violet light is refracted the most, so the angle change is the biggest one for violet, and you can see that at the bottom it has a shorter wavelength. Okay, one more bit to get through, and that's the critical angle. Let me move this up so we can see a bit more. Okay, I want you to imagine we have light inside of some glass, and it's travelling towards the surface of the glass where air is on the other side. Okay, now we know that air is a faster medium, so it moves away from the normal, so we get a bend in this direction. Okay, so that's just normal refraction at a boundary between two media. Now you know that if you were to increase that angle, so if I would send a ray in like this, the angle of refraction is bigger, because we know sine theta 1 and sine theta 2 are linked, it's a ratio. And you can see then that as we increase the angle of incidence, because this is the angle of incidence here, the angle of refraction, which is this one, also increases. There comes a point where there is a value of angle of incidence where the angle of refraction is at 90 degrees to the normal, and it's travelling along the boundary. Okay, so you can see this is my angle of incidence, the red angle here, and this is my angle of refraction, which is 90 degrees. The value of the angle of incidence that causes this to happen is called the critical angle. Okay, it's the angle that causes refraction at 90 degrees. If you exceed the critical angle, so if you send an angle of incidence that's even bigger than the critical angle, it will not refract, it will totally internally reflect. Okay, and that's, you're seeing the angle of incidence equals the angle of reflection. Okay, so the same rule applies for reflection inside of a more dense material. Okay, the difference between reflection and total internal reflection is this occurs inside a more dense object. Okay, total internal reflection happens inside of a more dense object, whereas with normal reflection, if this is my surface of my mirror, this is the back of my mirror, and my normal line's here, and it reflects like this, this is in a less dense medium that it's travelling in with normal reflection, because the mirror is more dense. Okay, but total internal reflection is a special case where it's trapped inside of the more dense object. And this is how fibre optic cables work. So internet can be sent using light pulses down fibre optic cables, and what they do is they send the light in at an angle greater than the critical angle of the fibre, and it bounces and reflects, totally internally reflects inside of the fibre, and it can travel very, very long distances, and then the light is seen at this end. And this is also how endoscopy works in medicine. So when surgeons want to see inside of a patient without having to do invasive surgery, you can send an endoscopy tube down. Light can be shone inside of an organ or inside of the body, and then light is sent back out using another fibre optic cable, and then the doctor can see that light and can see inside the patient. So the last thing I want to do is take Snell's law, n1 sine theta 1 equals n2 sine theta 2, and apply it to the critical angle situation. Okay, so to do that, we'll just quickly sketch out a critical angle scenario. So here's our glass here. Sorry, it's a bit wobbly, it's not my perfect drawing anymore. We've got light travelling in, sorry, I'm flashing my camera now, dearie me. Light is travelling in, here's the normal, into the boundary. This is the critical angle, which means that light will refract along the boundary, and this is 90 degrees. And I'm going to say that the glass is N1 and the air is N2, just in this particular instance. Now, it is a fact that the refractive index of air is 1. Okay, so N of air is 1, because we assume the speed of light in air to be the same as a vacuum, so C over V is 1. Okay, hopefully you can also see that this is N2, and theta 2 is 90 degrees. N glass, in this particular case, is N1, and theta 1 is the incident angle, okay, which in this case is the critical angle C. I'm going to sub these things into Snell's law. So I've got N1 sine theta 1, which is C, equals N2, which is 1, sine theta 2, which is 90. Okay? Now hopefully you know that sine 90 is 1 from maths. If you don't, I will teach you that separately. Okay, but I can express this as N1 sine C equals 1, because sine 90 is 1. Okay, I can rearrange that and say N1 is 1 over sine C. This is a very useful expression for you in the exam. If I'm going from a more dense to a less dense, N1 is 1 over sine of the critical angle. Okay, so fingers crossed that has helped you out a little bit with a lot of the waves stuff to do with light.